I welcome you all to the next lecture. Today, I'm going to discuss about the introduction to aerodynamics. It is the second unit of introduction to aerospace syllabus. Till now, what we have covered so far, we have covered the basic, definition of an aircraft. We have seen different kind of aircraft configurations. We have also seen the different motions of aircraft access systems. Parallelly, also we have gone through the exposure to the atmosphere, where you have given a flavor to how to calculate the local atmospheric properties at any altitude starting from mean sea level. Then followed by you have given an idea about different aircraft regulatory bodies like Federal Aviation Administration (DGCA), right, and JAA, etc. And apart from that, aircraft manufacturing companies were also discussed with you. So today I am going to start the topic, the basics of aerodynamics. As the name itself says, it's aerodynamics, right? Aerodynamics nothing but the study of fluid in motion, namely air, fluid, namely air in motion, and its effects on the physical bodies or physical structures. Those physical bodies may be either at rest or those may be moving in the fluid domain. And such kind of study is known as aerodynamics. And aerodynamics understanding is very much needed when we are designing any vehicle which is going to move in the air domain, like when we are designing the automotive car, or we are designing the wind turbine blades, or we are designing, let's suppose, gas turbine blades, as well as when we are designing the aircraft engine or complete aircraft. The basic understanding of aerodynamics is needed. So every vehicle which is going to expose to the air will be tested for aerodynamics. All right. So first it is ensured that it is aerodynamically, you know, optimized design. Then only we can go for prototyping the things, or we can start to manufacture the actual component or actual, you know, vehicle. So in this unit, basically you will be subjected to learn the properties of fluid. Basically we will be dealing only with air, because this is aerodynamics, we will dealing only with air. So air properties need to be discussed, and also we will see how actually air is going to interact with the objects, by what properties going to interact, by what properties going to stick over the surface of the object. Then we will see what all phenomena will happen, right, and finally what are the effects is going to create to the object, or whether what object is going to create effects to a steady air, right, if air is steady. So first we need to know what is fluid, right. This is a very basic definition everyone must know, because it's the foundation. What is the fluid? Fluid is something, if someone is there who doesn't know abcd about engineering, he will say fluid is something which is capable of flowing. Yes, the definition is also correct. Apart from that, technical definition, we can say fluid is a substance which undergoes continuous deformation when subjected to any tangential or shear stress, no matter how small that shear stress may be. Even with a negligible amount of shear stress, it will start deforming. So deformation is the inherent ability of a fluid. So example of fluid are liquid and gases. Both can be considered as fluid. So if you look at liquid, they are also capable of flowing, and gases are highly compressible, right? Even with the absence of very small, with the presence of very small pressure, they will be contracting or expanding, right? So they are highly compressible. That is known as fluid. Fluidity. Next, if we say fluid, next one is fluidity. Fluidity is nothing but the ability of flowing or ability of continuous deformation of fluid is known as fluidity. Then after that your flow comes. So flow is nothing but it is the act. It is the act of continuous deformation of fluid, which is known as flow. And in aerodynamics, basically, we will be dealing only with the flow. Now, flow may be of any type. There are various kind of flows, right? But main criteria start with ideal flow or real flow. When we are talking about ideal flow, right? Ideal flow is a flow which has no viscous effect, right? No surface tension and incompressible. That means we cannot compress that. This density is not going to vary. So these are the three parameters basically for ideal flow. We are talking about ideal flow. So ideal flow, viscosity is nil, right? No viscosity, right? Surface tension is also zero if it is a liquid, right? Liquid flow, and density is constant, incompressible, skid, right? And zero surface tension. If these three properties existing in a flow, that flow is known as ideal flow. None of the flow in nature is ideal flow, right? So ideal flow is a theoretical flow or hypothetical flow, but for some practical applications, we assume like water and air can be considered as an ideal fluid, right, for all practical purposes. But in reality, none of the fluid is an ideal fluid. So ideal fluid should satisfy these three conditions. Now next, go to the real fluid, which actually we usually deal with daily, day to day, uh, life. So what is basically a real fluid? Real fluid which is having a definite value of viscosity, because it will stick over the surface. Viscosity is something, right, which will resist the motion of layers of fluid when it's coming in contact with the solid surface. Viscosity, it will have some definite viscosity, it will have surface tension, right, it will be forming surface, free surface, and then finally it will be compressible. So density cannot be treated as constant for real flow or real fluid, right? So any fluid which is having a certain value of these parameters known as a real fluid. All natural fluids are real fluids, but when we are doing analysis of such kind of fluid, and we can make assumptions that it is equivalent to the ideal fluid, then we'll apply the equations, right, and to find out its behavior or characteristics. That clear? So this can be divided. So now, as I said, fluid is having two things, right? Liquids and gases. So if we compare liquids and gases as per the molecular spacing, we can say liquid molecules are slightly compact compared to the gases. Gases molecules are slightly far away situated. One thing based on that you can say, or you can say liquid will have certain volume, right? It will not have any shape, but gas particularly we say it is neither have volume and nor shape, right? Both things will not be existing for the gases, but for liquid certain volume will be there but no shape. That's another thing. Another, if you come to the liquid, liquid will form the free surface. If you fill the liquid, let's suppose water in a jug, it will forming the free surface, right? But gases, they do not form the free surface. Last but most important point is the volume of liquid does not vary significantly with the change of pressure and temperature, but gases are highly compressible. If you change a slight pressure, there will be a significant change in volume of gas. So gases are highly sensitive to those parameters, pressure and temperature change, but liquids, there will be very negligible change in volume when we are changing the pressure and temperature. That's just how we can differentiate between liquids and gases. So as I say, there is a flow. Now there is certain condition which we can say this flow maybe exists or may not, right? There are some condition it should satisfy. So every possible flow must satisfy the continuity equation. The basic definition of continuity equation you would have studied in your 10 plus 2, right? So that says it is nothing but law of conservation of mass. Mass cannot be created, not destroyed, it can be conserved only, right? So the detailed view of it in continuity is that mass flow rate remains constant throughout the flow domain, and we can say that as flow continuous, right? And that condition existing, then only we can say the flow which is given here is possible. If it is not going to satisfy the continuity equation, then it is not a possible case of fluid flow. So I'm going to drive a very small revision of continuity equation, how actually does it look like. So let's suppose consider a tube, right? I'm considering a tube. So this is a tube kind of section, right, through which this is one end. So if I say this is section 1 and this is section 2, and in this flow is taking place, right? So let's suppose the area here is A1, area here is A2, right? Inlet area A1, area A2. Let's suppose velocity by which flow is entering is V1 here, velocity by which it is leaving is V2 here. And we are assuming that, what we are assuming? We can assume or not. Let's suppose we are not assuming. We are saying flow is compressible here. So if I say flow is compressible here, then density 1 is here and density 2 is here. So rho 1 and rho 2, because that will also vary. So I am taking a generic statement flow. I do not know whether it's compressible or incompressible. So I consider both are variable, rho A1, A2. So starting point from here to here along the length, this is having certain length, I will say that is S, through which flow is taking place. Is it visible to you? Yes. So now if I apply the quantum concept, or this is open system basically. So if I fixed this boundary, I have fixed this boundary, this is my control volume. Now I'm looking at entry and exit, nothing is entering from this side. So whatever is happening, that is that entry and exit. So if I apply the mass flow, so if I say the mass which is entering, so first I need to define what is the mass flow. So as we know, density is defined as mass divided by volume, right? So mass, I can say density into volume, and volume is nothing but area into length. Usually we say area into length, particularly for this cross sectional area, we can say area into length. So if I say mass flow rate, that is m dot, that is m divided by t per unit time. This is rho into a into l by t. So length by time is nothing but this is called velocity, right? Velocity. So and this is m dot. M dot is a mass flow rate. So this is rho a into v, right? M is equal to rho a into v, right? Density, area, and velocity. This is the mass flow rate. So I can say the mass flow rate entering the section 1 right? So mass flow rate entering the section 1 just you can write in your word, mass flow rate entering the section 1 m dot 1 is given as rho 1 a1 v1, and mass flow rate exiting the section 2 is rho 2 a2 v2. So this is equation number 1, this is equation number 2. If there is no leak, there is no leakage, right, in this tube, then we can say whatever mass flow rate is entering into the system will be exactly equal to the mass flow rate exiting the system. There is no leakage because it's nothing, there's nothing is crossing the boundaries. So equating 1 and 2, I can say rho 1 a1 b1 is equal to rho 2 a2 b2. So this is my one equation, right? So this is applicable to any kind of flow, compressible, incompressible. So if I say it is incompressible, in that case my rho 1 will be exact equal to rho 2, but this equation is generic equation. So from here I can say this is nothing but density, area, velocity is equal to constant, right? Density, area, velocity is equal to constant. This is known as continuity equation applicable to compressible or incompressible. If I just say it is an incompressible flow, that means density will not have any value, with density is constant. So both side density can be cancelled out. So I can say A1 V1 is equal to A2 V2, or in general you can say area into velocity is equal to constant. Area into velocity is equal to constant. Very simple way you can say this. Area velocity is equal to constant. This is known as continuity equation. So if any flow is going to satisfy this equation, I will say that is the case of possible fluid flow. Is that clear? Now let's see, we will define one more parameter. As we have said, it is a flow, and flow need to be specified by certain parameters. So let's see what is that parameter is. So I am erasing this. So when we are specifying a flow, flow will be specified by its velocity component, and that velocity component means that resultant velocity vector. So we have to say vector because if we say three-dimensional flow, it will have three component of velocity. One will be varying in x direction, means along the flow, perpendicular flow, and sideways of the flow. So resultant velocity will be the summation of all these three velocity component. So there are two ways by which you can analyze an open system. One is called Lagrangian approach, right, and another is called Eulerian approach. Lagrangian approach used to say if we are analyzing any system, right, in which motion of flow is taking place, if I considering a unit volume of flow, and I will count total number of molecules present, and I am moving along the molecules, right? So if I fix certain lump of fluid, and that some 10 or 100 molecules are there, and if I'm moving along those molecules and I'm measuring the velocity and acceleration at different locations, and finally I will say these are the resultant velocity and acceleration of this given volume of the liquid. Such kind of study is called as Lagrangian way of study. But problem with this configuration, this kind of arrangement is it is very difficult to exactly say this is will be the overall behavior of the flow, right, by just capturing the motion of certain molecules, right, certain molecules, because if once you have selected certain molecules, you are moving along those molecules from one point to the another point, and finally you are saying that this is the resultant velocity and acceleration, but those will be applicable to those fixed values of molecules, but there will be hundred or thousands of molecules. So by studying some portion of molecules, we cannot exactly say this is the overall behavior of the flow. So it is usually we neglect, means we used to avoid that kind of study because it's very tedious. So then another fellow came, that is Eulerian. Euler gave an idea, why not we fix a station in the flow domain, where a person will be seated and he will be focusing on a certain area through which flow is moving. So at a single point he will measure the overall velocity and acceleration, so by which he can exactly say that this is the overall velocity and acceleration of a given volume of flow. So such kind of study is called overall study, or overall study in which we are not bothering about the individual molecule velocity and acceleration, right? And such kind of study is actually recommended because this will give you the exact flow behavior in a given domain. So in most of the engineering analysis, we follow the Eulerian approach, right, in which we are fixing certain volume, and that volume is surrounded by the boundary that is called control surface, and we are sitting just in front of that volume, and we are analyzing what is entering, what is going out, and finally by applying the energy balance, we are saying this is the net effect which is happening. And such kind of study is known as Eulerian way of study, and that is actually recommended. So as per the Eulerian, if I say this is the resultant velocity. The resultant velocity will have three components, right? X, Y, and Z. So it's a three-dimensional flow domain. If some flow is happening, that in real scenario, that will be 3D flow, and 3D flow means there may be property variation in all the three directions, right? So if I say at a single point, right, what is the velocity, that means it will be taking care of variation in all related to space coordinate as well as with respect to time. So velocity will be said as a function of space coordinates and time. What are the space coordinates? X, Y, Z, right? Only three space coordinate and time. So as per this, if I say velocity in x direction is small u, velocity in y direction is v, and velocity in z direction is w. So if I represent like this x, this is y, this is z. So velocity in x direction is u, and velocity component in y direction is v, and z direction is w, and all these velocities are the function of space coordinates. So these are the basically function 1 of x, y, z and t. Similarly, I can say this function 2 x, y, z and t, and this is function sum 3 x, y, z and t. So all these are the function of space coordinate and time. So if I am going to write the overall velocity, right? Overall velocity means resultant velocity, that will be nothing but in a very simple approximate way, I can say this. This is the velocity vector, which is ui, vj, and wk, where I is representation of x-axis. This is j, this is k, right? These are the vectors. This is resultant velocity vector. So if somebody asks you, right, what is the magnitude of it, you can say the magnitude of resultant velocity is nothing but under root u square, v square, and w square. So any flow, if we are specifying, will be specified by the velocity field. This is called velocity field. So it will be specify the velocity field. The moment I know the velocity field, I can find out the remaining parameters. I can find out the effect of this velocity. I can find out the pressure by applying the Bernoulli's equation. The moment I know the pressure, I can find out the remaining forces, right? Aerodynamic forces and all those can also be calculated. So as this is regarding the velocity field, right? And continuity equation got defined. Let's go for pressure now. So in aerodynamics, always we bother about the pressure distribution. So the moment we know the pressure distribution about a given object, right, I can find out the forces, right? And all the aerodynamic forces can be calculated. Lift, drag, side forces can be calculated, right, from the object if I know the pressure overall pressure distribution. So if I take the pressure distribution perpendicular to the flow direction like this, pressure balance, that will give the lift. If I considering the pressure difference along the flow direction, that will give the drag. If I am going opposite to that, sideways, that will give the side force. So that if unbalanced potential is there, respective force can be calculated the moment I have a clear idea about the pressure distribution. So let's go for pressure. So in order to understand the pressure distribution, usually we consider pressure coefficient. Pressure coefficient. So pressure coefficient is nothing but it's a non-dimensional representation of a pressure. So it is a very common practice to express the variables in non-dimensional. The moment we convert the variables in non-dimensional form, they will be independent of the local properties, right? So they will not depend exactly on local properties. So their value will be fixed at a certain point, and those value will be fixed. Those will be not a variable, right? So in aerodynamics, basically we always express the pressure in terms of non-dimensional form, that is called pressure coefficient. So pressure coefficient usually we say like if we define pressure coefficient, that is nothing but P naught minus P divided by half rho B square. So if you look at this equation, the P naught minus P is dynamic pressure, and dynamic pressure is nothing but basically half rho V square. This is also dynamic pressure. So dynamic pressure by dynamic pressure is non-dimensional term, right? And this is known as pressure coefficient. Pressure coefficient. So now we see the exact form, how does it look like. This is roughly we have said finally we come to know this is something different. So let's suppose there are 2 points right in the flow domain. These are the 2 points right in the flow domain, and flow is happening from this side. Let's suppose pressure here is P and velocity is V. Here pressure is something called okay, we say this is another pressure P1 and velocity is Q here, right? This is the domain. So here pressure is P, is it visible? Yeah, and this is velocity is capital V. Here pressure is P1, here this is the Q is the velocity. So we are going to apply the Bernoulli's equation between point here and point here, right? I can write the equation very simple way. This is P plus half rho V square, and assume that this is the flow domain in which density is constant. It's not going to vary in compressive flow domain. So I can write P2 P1 plus half rho Q square, right? So this equation can be written. So from here I can take P minus P1, this become P minus P1, and this thing I can take that side, so this will become half rho Q square, right, minus half rho B square. So you can take half rho B square as common, right? If you take that as a common, I can say yes, this is P minus P1, right, half rho B square, and this become Q divided by B whole square minus 1, right? I can write yes or no? Or usually yeah, so I have written in this way. So I have taken this as a common, right? P minus P1, this is half rho Q square, and this become like this. So same equation, I can write in this way: P1 minus P, right, is equal to half rho B square 1 minus Q divided by V whole square, Q divided by V whole square, 1 minus Q divided by V whole square. Take this half rho V square here, this will become Cp now. So this is P1 minus P divided by half rho B square, right, and is equal to 1 minus Q divided by V whole square, right. So I can write this equation. So basically this is nothing but this is Cp1, because the starting point pressure we are considering P1, and with respect to what we are considering with respect to P, and P is my free stream pressure. Here P is my free stream pressure. So with respect to that I am writing, so P1 minus P is nothing but Cp1, and this P is my reference. So dynamic pressure will be with respect to the reference velocity. Reference velocity is my capital V. So this Cp1 is equal to P1 minus P divided by half rho V square, that is nothing but minus Q by V. So from this equation say we can say Cp will be positive only when P1 is greater than P, and when P1 will be greater than P when my velocity Q is lesser than free stream velocity capital V. So the first observation from this, you can say Cp1 will be positive if Q is less than V or P1 is greater than P. This is the first observation that you can make out of this. Second observation, this will be negative only when P1 is lesser than P, that means Q is greater than V. So second observation, you can say Cp1 will be negative if Q is greater than V or P1 is less than P. The second thing you can say based on this equation of pressure coefficient. And third possibility is Cp1 will be 1 if Q is 0, right? Q is 0. That means final velocity at this point is becoming 0. If that is becoming 0, I can say Cp1 is equal to 1. That is only possible. The velocity will become 0 only when it is a stagnation point, right? So this Cp value is nothing but related to the stagnation point. So if somebody asks you what is the value of pressure coefficient at stagnation point, that will be 1. This is the maximum possible value of Cp. Then another thing you can do, Cp fourth condition, Cp will be 0, pressure coefficient will be 0. That is only possible if Q is equal to V, right? Or if I say P1 is equal to P, P1 is equal to P or Q is equal to V, a real scenario this thing will not happen. Nowhere final velocity will be equal to the initial velocity. But in some extreme conditions in vacuum, near vacuum, this condition may arise where Cp will become 0. That is only possible if my Q is becoming equal to V and P1 is equal to V. So if I am writing Cp1 as P1 minus P divided by half rho V square, then what will be this basically? This is nothing but Cp naught basically. This is Cp naught, pressure coefficient at a stagnation point. This is Cp naught basically, because P, this considered with respect to P naught, and reference is P, right? So this is Cp naught, this is Cp1. This is known as pressure coefficient. So this pressure coefficient knowledge is much needed, right, when we are dealing with the aerodynamics. Without the knowledge of this, you cannot proceed. One thing. So with the help of Cp, we can plot Cp at different locations, right? We can consider, let's suppose I will give you an overview of how actually we do that. So let's suppose this is an object which is moving, and over this object I will divide this, right, into n number of points. So these are the points, right? Here also point is there. So this is my free stream flow, which is pressure and velocity is V. And if I say this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, these are the 8 points over which I am going to find out the Cp values. So what I will do, I will apply the one velocity equation between this free stream and point 1, will get 1 Cp1. Then I will apply the one velocity equation similarly for point 2, I will get Cp2. With respect to 3, I will find out Cp3 and Cp4. Like that I will have n number of Cps, and those Cps can be plotted here, right? So if I say here velocity, if I say this is q1, this is q2, q3, q4, so I can directly say Cp1 is equal to p1 minus p divided by half rho v square. Cp2 is equal to p2 minus p divided by half rho b square. So this is nothing but 1 minus q1 by b whole square. This is 1 minus q2 by v whole square. Like that we can write the equations, right? Like that we can write the equation for Cp1, Cp2, Cp3, Cp4. The moment I know the values positive, negative, I can plot here. So I can plot like I can draw this. I can draw it here like this, and at the same point, if I get some value here 1, another is minus, another is 0.4, and here something minus 0.3, here minus 1 or minus 2, and here the point where flow is just striking stagnation point Cp1, and here also Cp1 where is leaving. So here 1 and 1, so I can connect like this. This is connecting here like this, and then I can connect 1 by 1, I can connect like this, right? Then finally it is becoming here 0, then connecting like this. So these all things what you are getting all around, this is known as pressure distribution. So Cp versus length, Cp versus chord length, you can draw that, and that is known as pressure distribution curve. The moment I know the pressure distribution curve, I can find out the aerodynamic forces. So this is the basic fundamental way of calculating the forces, right, in aerodynamics. So this is enough. Continuity equation got covered, and I gave you some flavor about the pressure distribution, how to calculate. So this is very small introduction about aerodynamics. And now I will cover some topics, right? Some people are having confusion which area need to be considered when we are finding out the aerodynamic characteristics of wing. So that concept I am going to cover now. So this I am stopping here. So how to do that? So this is an aircraft, roughly we draw like this, and this is the wing, right? This is the wing. Is it visible? Not visible. This is the wing basically. So there are two kind of areas. One is called wing planform area, another is called gross area. So when we are talking about wing planform area, That is nothing but the area of wing as viewed from the top. So we are viewing from the top of an aircraft, you will get some shape of aircraft wing, like it will be a rectangular wing, it will be a swept back wing, it will be a delta wing. If we calculate the area of the delta wing or that swept back wing, a rectangular wing, will that is known as wing planform area, right? So in most of the aerodynamic calculations, we consider the wing planform area, right? So that means wing which is attached here, and fuselage is also there, so it will be taking all the things including fuselage, right? This complete, if you are viewing from the top, we will get one plane form like this, and if you are calculating the area of that, that is called wing plane form area, that need to be considered for performance calculation. Second is called gross area, right? Wing gross area. So wing gross area, basically where we are excluding this fuselage section, only we are considering the wing actual area at both side, and we adding that is called gross wing area. So in practical, when we are doing the practical over the actual wing, we will be considering the wing gross area, but when performance calculation, we are actually considering total wing planform area, because here used to interact over entire thing including fuselage. So wing planform area. Now next thing is, what is the wing span basically? So wing span is nothing but from one wing tip to another wing tip. This total distance is known as wing span. Wing span is distance from one wing tip to the another wing tip. This is known as wing span. Now one more important terminology is called aspect ratio. What is aspect ratio basically? So the cross section of wing is nothing but airfoil, right? So this is airfoil. It's not visible. So airfoil, and airfoil is having chord length, right? This is the chord length. So this is the chord length basically. This is the airfoil shape. So aspect ratio is nothing but the ratio of wing span to the chord. So wing span is this, right? And chord is this. If you divide this, this will become aspect ratio. AR is equal to wing span divided by chords. Very simple definition. This is known as aspect ratio. This is known as aspect ratio. Wing span to the chord length is known as aspect ratio. So for different aircraft, wing aspect ratio will be different. It will be varying between 6 to 16, right? If we are going for what we say, sports aircraft which is having a rectangular wing, their aspect ratio may be nearby 14 or 12. If you are going for a fighter plane, right, where we need complex, very compact design, aspect ratio will be between 6 and 8, between 6 and 8. And for all general aviation aircraft, right, or sports aircraft, we are basically using larger wingspan, and we are going for larger wingspan, aspect ratio will more. That will be ranging between 10 to 16, maximum 16. Beyond that you cannot go. And another thing, if higher the aspect ratio, higher the lift, but there is a threshold value. If you are going for very large wingspan, if we are flying at very high altitude, due to this gust of wind, structural damage may occur to the wing. So that's why there is a limitation. We cannot cross certain aspect ratio. So in fighter plane, hardly we can go to the aspect ratio 8, not beyond that, because fighter planes are used to fly at very high speed and high altitude. And if you are going to very high altitude, structural problems will be more because of the presence of this gust circulatory flow of air. So we usually avoid that, to use higher aspect ratio wing in the fighter plane. So there it is 6 to 8, and here sports aircraft we can go up to 16, right? But usually it's not recommended. It may be somewhere 10 and 12. And passenger aircraft will be somewhere in the intermediate, right, between 6 to 12. Something can be used in the passenger aircraft or in transport aircraft. Aspect ratio will be something like this. Aspect ratio and wingspan, that is clear. So with this I am closing today discussion, right? In next class I will be discussing about the boundary layer concept, right? What is the boundary layer? Because boundary layer is very much needed, right? Then only there will be flow, attachment and detachment over the surface. When there is no attachment of the flow, there will be no defect over the object, right? So in order to understand the effect, there should be attachment. Attachment will happen due to the properties of fluid, that is called viscosity basically. So every liquid or gas, every fluid is having certain value of viscosity. Because of that, it used to interact with the object. The moment the flow will attach, then only some pressure distribution will develop, and based on pressure distribution, exactly we can say this effect is going to create to the given object, right? So today this much is enough. So I'm closing my discussion here, right? So if you are having any doubt in this, you can contact to me at any time. So thanks for your patience for listening this lecture. So if you find this content useful, please like, subscribe, write, and share this content among your friends. Thank you very much. Have a nice day.